Picture a humming room filled with black racks and pulsing cables where the light feels like late afternoon at sea. Warm on the edges, cold in the core. Air slips over metal heat sinks as fans push a steady wind. Inside each server, a slice of silicon the size of a playing card moves trillions of numbers at once. Outside that room, entire product roadmaps, research labs, and national strategies wait in line. In every tech cycle, there's a bottleneck that decides who moves and who stalls. In this one, the bottleneck is the GPU. Not because it's fashionable, but because it is the only widely available machine that turns massive piles of data into working intelligence at speed. In the next few minutes, we'll open the box and show you why these chips became the tollbooth of modern AI, how money and software lock them in place, why memory and networking, not just raw compute, set the pace, and what it means for the companies racing to build the future. If you want to understand this moment, follow the bottleneck. It leads straight to the GPU. The story starts far from AI hype. Graphics processing units were born to draw pixels, triangles, textures, and shadows for games and films. Their trick was simple: do many similar math operations in parallel. When researchers discovered that the same pattern, matrix math over and over, drives neural networks, a door swung open. In the late 2000s, NVIDIA, bet the company on general-purpose GPU computing, building a software stack called CUDA, K-O-D-A, so developers could program these chips like flexible math engines. The bet looked quixotic until deep learning hit a milestone and models outgrew CPUs. From image recognition to language, success came from scale. More data, bigger models, more compute. Data centers adapted. Racks once optimized for web servers began to host dense accelerators, liquid-cooled blocks, and high-speed fabrics that stitch thousands of GPUs into one enormous computer. Why it matters today is not abstract. Every product that promises generative features, summaries, images, code, search, copilots, depends on training and running neural networks. Training is the uphill climb. Inference is the daily commute. Both are shaped by hardware limits. Government agendas now include sovereign AI as a strategic resource. Investors treat supply of accelerators like oil capacity. The GPU sits at the intersection of science, infrastructure, and profit. At the heart of the GPU advantage is parallelism. A modern neural network is a stack of linear algebra operations: multiply, add, repeat. A GPU contains thousands of small cores tuned for these operations, plus specialized units that accelerate tensor math. But raw cores don't win alone. Feeding them data fast enough is the real art. That is where HBM, or high bandwidth memory, changes the game. HBM stacks memory chips vertically right next to the processor and connects them with ultra-wide buses. Think of it as replacing a single-lane road with a dozen multi-lane highways. Bandwidth per watt surges, latency drops, and the GPU stops waiting on memory. This proximity is achieved with advanced packaging, like TSMC's, Taiwan Semiconductor Manufacturing Company. CoWoS, which mounts memory and compute on a shared substrate. Packaging isn't glamorous, but it's the hinge of the system. If CoWoS capacity is tight or HBM yields dip, the entire supply chain slows. Even when the chip design is ready, systems cannot ship in volume without the memory stacks and packaging slots to assemble them. Scale transforms a GPU from a fast chip into a building block of a supercomputer. A single accelerator is powerful, but today's frontier models train on thousands. That makes the network a second bottleneck. Interconnects like NVLink inside a node and high-speed fabrics across nodes, InfiniBand or Ethernet with RDMA, decide how efficiently the cluster behaves like one large machine. Imagine a restaurant kitchen with star chefs who can cook 10 dishes at once. If the waitstaff can't move plates through the door, the dining room starves. In AI clusters, poor networking forces chips to idle, devouring power without progress. This is why vendors sell whole systems. placed GPUs, memory, interconnects, and software tuned as a unit. At that layer, seemingly small choices, topology, cable length, switch buffers, translate into weeks saved or wasted during training runs. Follow the money and the picture clarifies. Hyperscalers, big cloud platforms and large consumer internet firms, rent or buy GPUs by the tens of thousands. The business model is a stack. At the bottom, chip designers capture outsized gross margins on scarce, best-in-class parts. Foundries like TSMC convert wafers into compute using extreme ultraviolet lithography tools from companies like ASML, while packaging lines bond HBM to logic. Memory vendors such as SK Hynix, Samsung, and Micron supply the stacks that define bandwidth. System makers integrate boards and cooling. Networking suppliers move data. Then cloud providers wrap the whole thing in services and APIs, charging by the hour, by the token, or by the model call. The customer, startups, enterprises, labs, converts that spend into product features and research milestones. In theory, competition at each layer pushes prices down. In practice, the bottlenecks reverse the flow. Whoever controls the scarcest layer commands the terms. The software story is as important as the silicon. CUDA became a de facto standard by lowering friction. Developers could write once and inherit optimized kernels for each new GPU generation. Libraries surfaced dense math and communication patterns so research teams could focus on models rather than plumbing. Frameworks like PyTorch and TensorFlow met the hardware halfway. Over time, an ecosystem formed: compilers, profilers, schedulers, distributed training libraries. This is the gravity well that keeps workloads on GPUs even as alternatives emerge. AMD's software stack, ROCm, has matured, and cloud-native compilers now target multiple backends. But the path of least resistance, especially when timelines are short and talent is scarce, still runs through the incumbent S libraries and tools. Switching is possible, switching under pressure is rare. History hinged on a handful of decisions. One was the original platform bet. NVIDIA's leadership, including Jensen Huang, Chua Akeng, chose to build for general compute long before AI's commercial payoffs were obvious. That meant years of investment in drivers, kernels, and partnerships without immediate returns. A second hinge was the arrival of tensor cores, specialized units that accelerate the matrix operations at the heart of deep learning. When these landed alongside mature software, a feedback loop began. Better hardware enabled bigger models. Bigger models demanded better hardware. A third hinge was interconnect strategy. Acquiring Mellanox, brought networking stack control in-house, allowing coherent systems tuned from chip to switch. Owning the fabric matters when your customers train models across tens of thousands of accelerators. Buyers made their own pivotal choices. Cloud platforms decided whether to build proprietary accelerators or double down on merchant GPUs. Building custom silicon can cut cost over the long run and reduce vendor lock-in. But it demands design expertise, software compatibility, and the patience to ride multiple silicon generations. Opting for merchant GPUs offers time to market and a broad developer base at the cost of reliance on external roadmaps and pricing. Many picked a hybrid path, their own chips for specific workloads plus vast GPU fleets for everything else. Meanwhile, enterprises had to choose whether to chase the frontier, state-of-the-art models that require enormous clusters, or to right-size with smaller domain-specific models on fewer nodes. The first path promises leadership and headline performance. The second aims at business efficiency and control. Supply chain decisions created visible trade-offs. Expanding packaging capacity is expensive, slow, and sensitive to yield. Memory vendors had to commit to HBM lines years in advance, balancing risk against the possibility of a downturn. Networking teams faced an InfiniBand versus Ethernet decision with cultural as well as technical dimensions. InfiniBand offered a proven path for low-latency training at scale. Ethernet promised ubiquity and rapid iteration in software. Organizations also confronted power and cooling realities. Packing more accelerators into a rack raises power density. Air is no longer enough at the frontier. Liquid cooling arrives with its own costs and operational learning curves. Facilities designed for web traffic found themselves updating transformers, chillers, and floor plans. Every choice echoed the same logic. In a scarcity cycle, control of the bottleneck, memory, packaging, networking, energy becomes strategy. The consequences rolled through balance sheets. Prices for top accelerators climbed and lead times lengthened. Capital expenditure at hyperscalers soared as they committed to multi-year compute build-outs. Because demand concentrated on a few performance leaders, margins pooled upstream. Memory suppliers with competitive HBM captured windfalls. Packaging slots became as valuable as wafers. Networking portfolios reported record orders as clusters scaled. Cloud providers faced a new profitability puzzle, offering AI services that attracted customers while shielding their own margins from the cost of scarce hardware. Startups felt the constraints most viscerally. In earlier eras, a great team and a laptop could build an internet-scale service on rented infrastructure. In this cycle, the frontier often requires access to compute budgets measured in millions and relationships strong enough to secure capacity. Some companies solved the constraint with capital, others pivoted to smaller, more efficient models. A few traded equity for compute credits, turning access to GPUs into the new seed money. Market structure tilted toward power law outcomes. Where performance compounds and ecosystems lock in, leaders pull away. But competition did not vanish. AMD pushed hard with accelerators that target high memory capacity and strong interconnect bandwidth, courting customers who value open ecosystems and price performance. Intel's Gaudi line offered another vector, particularly for training and inference clusters where software support sufficed and network economics worked. Cloud-native alternatives, like proprietary training chips, gained traction inside their own services. These options pressured prices and reduced single-vendor risk, even as the incumbent maintained lead position in developer mindshare and system breadth. The broader economy felt second-order effects. Regions with abundant power and cool climates attracted data center investment. Municipalities weighed water usage and grid load against jobs and tax bases. Universities adjusted curricula to the new balance between systems engineering and model science. The modern echoes are everywhere. Generative features in office suites, search engines, and creative tools ride inference fleets that look unlike the training clusters but share the same constraints. Inference cares as much about latency and cost per request as it does about peak throughput. That means memory capacity and networking are still decisive, but software efficiency becomes king. Quantization, sparsity, and clever batching shrink the hardware footprint needed to support massive user bases. Many enterprises now pilot smaller models trained on proprietary data that fit within a few racks rather than a few halls. Sovereign AI has become a phrase of art. Governments and national labs are assembling their own clusters to retain control over critical infrastructure and sensitive data sets. In parallel, the industry confronts the physics of scale. Power budgets push past historical norms. Liquid cooling moves from exotic to expected. Even the shape of racks changes, with pre-integrated cabinets complete with networking and power distribution shipped as units. The frontier now includes not only bigger models, but smarter ways to use silicon, memory, and energy. There are real limits and honest critiques. Calling GPUs the new oil works as a metaphor for scarcity and leverage, but it misses important differences. Oil is fungible, stored, and burned once. Compute is a capability that improves with software and can be reused infinitely. Still, bottlenecks behave like commodities when demand outruns supply. Another nuance is that GPUs are not the only path. Custom accelerators, like Google ASTPUs or cloud-specific training chips, show that workload-specific designs can win on cost or performance. If software abstractions keep improving, the developer moat narrows. There is also a memory wall. As models grow, moving data becomes more expensive than the math itself. Innovation at the memory and interconnect layers may matter more than incremental gains in raw flops. Reliability and reproducibility pose quieter constraints. Training runs that span thousands of devices multiply the ways something can go wrong. Debugging distributed systems takes scarce expertise. Geopolitics adds uncertainty in export controls and supply concentration. None of these end the GPU era, but they shape its slope. From this story, a practical playbook emerges. First, follow bandwidth. In many AI workloads, memory speed and network throughput determine real performance more than peak compute. When evaluating systems, ask how often the chip waits. Second, own the bottleneck you can influence. If you cannot secure top-end accelerators, design for efficiency. Smaller models, better data curation, smarter compilers, and caching that cuts redundant work. Third, treat software as leverage. The team that understands kernels, graph optimizations, and communication patterns can turn yesterday's hardware into today's advantage. Fourth, diversify exposure. Blended fleets, merchant GPUs plus alternative accelerators reduce single-supplier risk and let you match hardware to workload. Fifth, mind power and cooling early. The cheapest kilowatt-hour is the one you design around, not the one you buy later. Site selection and cooling strategy are product decisions in disguise. Finally, invest in portability. Models, data pipelines, and orchestration that can move across clusters and vendors keep you nimble in a market that shifts faster than procurement cycles. We began with a room full of racks and a line of people waiting outside. The promise was to explain how GPUs became the tollbooth of modern AI and why the true constraints, memory, packaging, and networks, decide who moves and who stalls. Now you've seen the engine up close. Parallel math makes the GPU fast. Proximity to memory keeps it fed. Fabrics bind chips into one machine. Software makes it usable. And scarcity sets the price. As long as those conditions hold, accelerators will feel like a strategic resource, not a commodity. The next chapters will likely be written at the edges. Lower power inference, smarter compilers, denser memory, and new interconnects, where efficiency beats brute force. If you build or invest in this space, ask one simple question at every turn. Where is the bottleneck now, and who controls it? That answer will tell you who captures the next dollar of value, and how far the line outside that humming room will stretch.